Before we tackle the topic of the difference of two means using a t-test, we need to come up with a way of evaluating the difference of these two means. We do this by developing the process of hypothesis testing. Hypothesis testing is our first real link to inferential statistics. Hopefully you remember all the material on the central limits theorem and the development of a distribution based on chance. Now we're going to develop a way of looking at our information to see whether there are significant differences. And by significant, I mean statistically significant. All of our research begins with what we call the null hypothesis. It's an assumption about the way the world operates that may or may not be true. It's the assumption that chance is operating. For example, if I take a sample of men and a sample of women, and I measure their income and calculate average income for men and average income for women, I may observe a difference between the two of them, between those two averages. The null hypothesis assumption is that the differences I observe are due to chance, or in my case, sampling error. If those differences are sufficiently large, at some point I will reject the null hypothesis and conclude that some alternative hypothesis is a better fit for my data. So once we establish the null hypothesis, we then go out and collect data to test the viability of that particular hypothesis. If the data are different than what we would expect given the assumption of chance, then we're going to reject the null hypothesis and conclude that some alternative is probably correct. If the data are very similar to what we would expect under the assumption of the null hypothesis, then we're going to fail to reject the null hypothesis. Or another way of saying this is that our hypothesis is not rejected. We get into some funny language here. We'd like to be able to say that we reject the null hypothesis or that we accept the null hypothesis. But we're unable to say accept the null hypothesis because doing that, there's the possibility of committing the fallacy of affirming the consequent. In my example here, I have a theory that says it has three propositions. Proposition number one, all people will conform to all norms of their society. That's the thing we'd like to know. Proposition number two, it's a norm of society X not to steal. Proposition 3. Jones is a member of society X. We can't really know number one unless we examine the entire population, which we typically can't do. On the other hand, if we note that Jones steals, we can reject hypothesis number one. On the other hand, if Jones does not steal, we can't say that that proposition number one is true, because it's possible that Jones is just simply not a thief. So we get into this kind of funny language where we have to say we can clearly reject the null hypothesis or we can fail to reject it. When we do hypothesis testing, we're looking for the answer to this question. What produces the differences between our observed and our expected values? And there's two possibilities. First, there actually is a difference. For example, again, comparing average income for men to average income for women, there may actually be a difference between those two averages that is statistically and substantively important. And hopefully my test of significance set up in my hypothesis test will capture that difference and identify that difference. On the other hand, an alternative explanation is that whatever difference I observe is due to chance. In this case, it would be random error or sampling error. There's 5 steps to hypothesis testing, and in this course we're going to ask that whenever you see on an exam or a homework to do a hypothesis test, you detail these 5 steps. It's not really that difficult to do, it becomes a bit mechanical, but we're just trying to enforce the idea that behind every hypothesis test are these 5 concepts, these 5 things. So step number 1, we make an assumption about the world. We assume that the null hypothesis or the hypothesis of no difference is true and that chance is operating. Step number 2, you have to know what the range of outcomes looks like if the null hypothesis is true. You have to know what chance looks like. Now, if you think back to our central limits theorem discussion, you'll remember that I made the statement that the central limits theorem provides us a distribution, the sampling distribution, which is a picture of chance. There's a different sampling distribution for different statistics. The one sampling distribution we've used so far is the t distribution or the z distribution. There are other sampling distributions as well, each one of which is a picture of how chance operates on that particular statistic. So in step 2, when you're doing a problem, you have to identify the appropriate sampling distribution to use. Right now, that's very simple. We're going to use the t-distribution. Step 3, you have to decide how much evidence you need to reject the null, and we call this the alpha value. You also have to decide if you're going to do a one or two-tailed test. Let's first talk about this one versus two-tailed test. I believe that you should be able to do a one-tailed test. Many people do not. For the sake of keeping this part of the course a little bit easy, and also to fit in with what goes on practically in the world when people submit articles for publication, I'm going to recommend at this point you always use a two-tailed test and not use a one-tailed test. You'll get more details about this when you take another course in statistics. So for now, we'll assume we'll do a two-tailed test. The alpha level also can be a bit tricky. What we're talking about here is how big a difference do you need to reject the null? How big a departure from normal, how big a departure from chance do you need to reject the null hypothesis? And that's a bit more difficult. You'll remember that earlier in the class when we were looking at the z-distribution and understanding it as a probability distribution, I said that there are 3 criteria that most people use to identify typical from atypical things. Those 3 z-scores are 1.96, 2.58, and 3.3. The associated area in the tails of the distribution for a two-tailed test are 0.05, 0.01, and 0.001. Those 3 numbers, 0.5, 0.1, and 0.001, are the alpha values. As a researcher, you need to decide which of those values is appropriate for your particular problem. If you don't demand as much evidence, you can use a larger alpha value, for example 0.05 compared to 0.001. If you need more evidence to reject the null, a bigger difference, a greater departure from chance, then you're going to want to select an alpha value like 0.001 compared to 0.05. Steps 1, 2, and 3 are all done before you actually go out to the world and collect any data or do any work. That is, you can do this as a thought problem. Step number 4, which is not covered fully in this course, is you have to go to the real world and collect some data and calculate some sample statistic. So this is where the merging of statistics and methodology come together. In another class on methodology, you're going to learn how data are produced. And in this statistics class, you're learning how statistics are produced from those data. We're going to assume that we already have data, and for this class, we've been using the General Social Survey. Here we need to calculate a particular statistic, and at this part of the course, we're going to calculate a t-statistic. The last step. Step number 5, you have to make a decision. Do you reject the null or fail to reject the null? What you do is you compare the statistic you calculated in step number 4 to some statistic that is developed by chance that you get from a table in the back of the book. We've shown you the Z table, we've shown you the T table. Those tables represent different places of chance on those different distributions, T and Z distributions. This will be clear when we actually do an example, but for now, just understand that our sampling distribution provides a picture of chance. We observe something in the real world and calculate a statistic to represent what we observe, and then we compare what we observe to what we should observe if chance is operating, if the null hypothesis is true. That's step number 5. And then we make a decision to reject the null or fail to reject the null. Okay, let's look a little more detail about one versus two-tailed tests, even though I've argued that we're going to be spending most of our time with two-tailed tests. For the null hypothesis, this is one way you can write this symbolically. H sub 0 colon, the null hypothesis, is equal to mu sub y equals 0. So for example, we're saying here that the population mean is equal to 0. You can also state it as a difference. For example, the null hypothesis could be that mu sub 1 minus mu sub 2 is equal to 0. That would be consistent with the example I've talked about, where if we had average income for men and average income for women, and we looked at the difference. We would assume if there's no difference across gender, that if we took the mean of men and the mean of women and calculated the difference, it would be 0. Of course, we may observe small differences from 0, And that's what our test will differentiate. How small is that difference, or how big does it need to be to reject the null? Now we need an alternative hypothesis. The two-tailed alternative is given as h sub 1, and here you can see I've listed it as mu sub 1 minus mu sub 2 is not equal to 0. That is, I'm not saying in advance that men make more money than women or men make less money than women. I'm just saying that men and women make different amounts of money on average. That's a two-tailed test. We're not predicting a direction. If I want to do a one-tailed test, I actually predict a direction, and I might say that I believe, before I do my statistical test, that men make more money than women. And if my mean for men is mu sub 1 and my mean for women is mu sub 2, then my one-tailed alternative hypothesis is mu sub 1 minus mu sub 2 is greater than 0. If for some reason I had reversed those means, there's nothing wrong with that, such that mu sub 1 was the average income for women and mu sub 2 was the average income for men, then my alternative hypothesis would be mu sub 1 minus mu sub 2 is less than 0. That is, it's negative. The null and the alternative are the two outcomes that we're going to decide between. Now the table at the bottom shows the different t-scores or z-scores for large samples when alpha equals 0.05, 0.01, and 0.001. Let's just concentrate on the shaded in area for the two-tailed test. These numbers should be very familiar to you. If alpha is 0.05 two-tail, it means that 2.5% of the distribution is in the right tail and 2.5% is in the left tail, and that 95% is in between those two tails. If a score falls plus or minus 1.96 standard deviations around the mean, that's in the middle 95% of the distribution. Any z-score or t-score that exceeds 1.96 would be considered atypical or statistically rare. You can see that the t or z scores go from 1.96 to 2.58 to 3.29, which I sometimes round to 3.3. And that's associated with more departure from chance, alpha 0.01, alpha 0.001. Now, this graph is something you see in a lot of different textbooks, and it describes the decision-making process and the kinds of errors we could make. The columns are labeled true and false, and that whole top is called the true state of affairs in the universe. And what I mean by this is, if we could know what's going on in the universe at the level of the population, we would know whether the null hypothesis is true or false. Without question, we'd be able to make a decision that the null hypothesis is true or false. That's the true state of affairs in the universe. But I've taken a sample, and from that sample, I'm going to make a decision about whether the null is true or false, and I may or may not be right. That decision based on a sample is subject to error. Now, if you look at this diagram, I could reject the null hypothesis. If I reject the null hypothesis based on my sample, and it's actually false, then I get a little smiley face up there in that one box. That means I've made an okay or a good decision. On the other hand, if I fail to reject the null hypothesis, that is, what I observe is pretty similar to chance, and the null hypothesis is actually true, again, I've made a good decision, and I get a little smiley face down there in my okay. Those two cells are good decisions. The truth is, I don't actually know whether I've made a good decision or not because I don't have access to the true state of affairs in the universe. But I can also make an error in hypothesis testing, and there's two different kinds of errors I can make. The first kind of error is called a type 1 error. This is when I reject the null hypothesis based on my sample, when in fact the null hypothesis is true. That is, I conclude that what I observe is different from chance, but it's not. Chance is operating, but I conclude that it's a variable. I believe that it's a variable. I also can make a type 2 error. Now, type 1 is often called alpha error. Type 2 is often called a beta error. I just like to call them type 1 and type 2. Type 2 error is when I fail to reject the null hypothesis when in fact I should. The null hypothesis is actually false. So that a variable is operating. There really is a difference or a deviation from chance, but I believe that it's due to chance. If you look at the little cartoon thing up the right, you'll see that a type 1 error in the medical world is called a false positive, and a type 2 error is a false negative. You can't control the probability of making a type 2 error very well. In another class, you'll probably learn that there's 5 different kinds of things that affect the probability of making a type 2 error. We're not going to pay much attention to that now because it's really beyond our control, at least in this class. But you can control very precisely the probability of making a type 1 error. You'll notice that a type 1 error is also called an alpha error. And you get to determine the probability of making a type 1 error by how you set the alpha value. Alpha 0.05 means if you reject the null hypothesis, there's a 0.05 probability that you have done so incorrectly. If you use alpha 0.001 and you reject the null hypothesis, it means that the probability that you have made a type 1 error is 0.001. So the researcher can very directly control the probability of a type 1 error, but can only indirectly control the probability of a type 2 error. Here's a little spoiler alert. One of the biggest determinants of making a type 2 error is your sample size. And since we're using the General Social Survey, we can't increase our sample size to reduce the probability of a type 2 error, which is part of the reason I'm glossing this over a little bit. We're going to look at 2 problems here. I call this a funny problem. It's a funny problem because if you look at the information I have the mean of the population, 100. I have the standard deviation of the population, 15. That is, I have mu sub y and sigma sub y, respectively. That's pretty unusual to have that information. That's funny. I also have the sample mean, 103, and the sample standard deviation, 12, y bar and s sub y, respectively. And that's based on a sample of size 300. So let's talk about what would be typical or atypical. Is a score of 103, a mean of 103, statistically significantly different than the population mean of 100? Step number 1, assume the null hypothesis is true. That is, we'll assume that 103 and 100 are close enough to each other that any difference we observe is due to sampling error and not to an actual difference. Step number 2, we need to have an idea about the range of possible outcomes, and we have to pick an appropriate sampling distribution. The sampling distribution I'm going to pick here is a z-score. I can pick the z distribution and not the t distribution because I have the population standard deviation. That's what makes this kind of an unusual or funny problem. I'm going to set my alpha value to 0.05. That means that I have 2.5% of the distribution in each tail, the left and right tail. And I'm going to shade in on that diagram in the upper right. I'm going to shade in the area that exceeds 1.96 and minus 1.96. Any test statistic I see that falls in that region, it's called the critical region, will lead me to reject the null hypothesis. Step number 3, how much evidence do I need? Again, this is our alpha value, 0.05. Step number 4, go to the real world, collect our data, and calculate some sample statistic. So here's the sample statistic I'm going to calculate. I'm going to calculate the difference between these 2 means, the population mean of 103 and the sample mean of 100, and I'm going to divide that by the standard error to put this into a z-score metric. When I do that calculation, I get a value of 3.46. The interpretation of this is that the mean of 103 falls 3.46 standard deviations above the mean of 100. Step number 5, we have to compare 4 with 3. That is, we have to compare the 3.46 with the 1.96. You'll notice I've drawn a vertical dashed line that is right at 3.46. You can see that it clearly falls in the critical region, that it exceeds 1.96. And therefore, I'm going to conclude that this particular difference, this 3-point difference between 100 and 103, is statistically significant, and I'm going to reject the null hypothesis. If we had done a one-tailed test, our critical value in step 3 would not be 1.96, it would be 1.64. That's shaded in area, is also 5% or 0.05 of the entire distribution, but it's all piled up into one tail, where in the two-tailed test it's divided equally between the two tails. In this particular problem, it doesn't make a difference. I would reject the null whether I was doing a one- or two-tailed test. Let's look at funny problem number 2. Notice that I've got roughly the same information. The only piece of information I'm missing here is I do not have the population standard deviation. I've got mu sub y equals 80, that's the mean of the population. I have y bar equals 83, and the standard deviation of y equals 9, based on a sample size of 60. Now this is a bit of a funny problem too, because while I have the mean of the population, I don't have the standard deviation, and again, typically we won't have the mean of the population. That's what makes this kind of an odd or unusual problem. Now let's go ahead and calculate our z statistic. We're going to use the same setup as before. We'll assume the null hypothesis that 80 and 83 are basically only different because of sampling differences, sampling error. We need a picture of chance. We're going to use the t-distribution here. Why do I use t, not z? Because I don't have the population standard deviation. If I don't have the population standard deviation, I really need to use the t-distribution. And the t-distribution allows for the greater error involved with estimating the standard deviation of the population. Step number 3, I'm going to go ahead and use the same alpha value, alpha 0.05, and step number 4, we go and calculate our statistic. Notice that the statistic is calculated in an identical fashion. The numerator is just the difference of the two means, and I'm dividing by the standard error here. But notice that I don't actually use the population standard deviation because I don't have it. I'm going to use my estimate of the population standard deviation, S sub y, or in this case 9. When I calculate this statistic, I get a value of 2.58, and I exceed my critical value of 2.0. Now, you might wonder, well, why are we using 2.0 and not 1.96? We've always used 1.96 when we have this alpha 0.05 two-tailed. And the answer to that is that the t-score varies by sample size. Smaller samples have larger t-values than if you were using a z-score. I have to use t-scores here because I don't have the population standard deviation. And where did I get that value of 2? There's a table in the back of your book. I look up two-tailed alpha 0.05 with 60 degrees of freedom, and I can read off that table the value of 2.0. That is, the critical value is plus or minus 2.0. I hope this helps, and we'll of course talk about this in class. If you have any problems, I suggest going back and looking over the central limits theorem videos again and notes, and watching this video one more time. We'll see everybody in class.